Take it away.
All right. Go ahead, Victor. Did you want to say something?
No, I said we were all good. We can start.
All good. All right. So, hello, everyone. Thank you for making time for me and for us on Friday afternoon. My name is Yuval. I'm also known as the Qubit guy, at least on Twitter. That's used to be my algorithm for entering new markets. Because quantum is new. Before that, I did virtual reality, and I was VR guy, and then I did wireless power, and then I was charge guy. So the fact that Qubit guy was available made sense to me to get into quantum. I'm the chief marketing officer of Classiq. We are a company based in Israel with offices in the US. By way of education, I have a master's degree in physics and also an MBA from Northwestern. So my mom thinks I'm a failure because I don't have a PhD, but it may be too late to fix that. And today I wanted to talk to you about what we see as the issues in creating larger scale quantum software algorithms and why we think we have a solution and what that solution might be. I've seen these slides before, so this is for you. So please hit me with questions anytime you want. Victor, you can probably help me because I'm not sure I can see the chat screen, the chat window on my.
I will moderate a chat.
So, but please, whenever you want, just hit me up. So, just about Classiq, started just over 2 years ago. Today, we've got about 35 quantum software engineers and scientists. We've raised about $50 million to date. This is not Photoshop. This is a nice picture from Times Square from a few weeks ago when we announced our Series B. Customers in various industries, financial services, defense, and others, and working with lots of different universities these days and hoping to extend that this year. You may have seen the results of this survey. This is a survey that was done in December of last year and was asking about where enterprises are in their quantum computing adoption. And it was very heartening to say that about 30% are in early or advanced stages of looking into quantum. You see many logos on the right, whether it's automotive or financial services or energy or others. These are all companies that have quantum teams that are looking at ways to utilize quantum. We know that quantum is early, but I think these companies know that you have to crawl before you walk and walk before you run. So they want to build the confidence and the expertise internally before they deploy quantum in mission critical applications. So we're at an early stage of the market. But to be ready, you need hardware and you need software. Hardware these days is usually hosted on the cloud, but hardware without software is just as useless as software without hardware. They need to work together. They need to complement each other. But the problems that we see is that when you had 4, 5, 7 qubits, you could create a circuit manually. You could say, I want this qubit to go to this gate, and this gate to go here, and so on and so on. And several thousand people in the world can do that with 5 qubits. You get 25 qubits, maybe a couple hundred people can do circuits that make sense, that are efficient, that are not trivial circuits. And when you get to 250 or 500 or 1,000 qubits, it just becomes hopeless. You cannot do it manually. Just like many people can run a 100-meter dash in under 20 seconds, and very few can run in under 10 seconds, and no one can run in under 5 seconds. So we need a better way. Just like people today no longer write, or most people no longer write code in assembly or no longer create raw HTML pages, we need a higher level way of creating quantum software that makes sense. And so we sometimes see that we think it's not rocket science, but certainly sometimes feels like it. So when companies go and want to do a quantum project, they usually, at least in our experience, start from an article that they saw. This is, for instance, an article that was published some time ago about how to use quantum in derivative pricing and in pricing financial options. And it's done by Goldman Sachs, who's got a large quantum team, and University of Maryland and IBM. And it's a fairly long article, and then it has a recipe. Basically says, okay, well, this is what you need to do to implement our algorithm. And let's even say that they told you the truth, the whole truth, and nothing but the truth. This is truly the algorithm. Now, so what people end up doing is they go to every single step. Step number 8, we then take care of timestamp C by adding this function to each register C controlled on the Tth qubit of cap T. So every step is an adventure. How do you implement that in a qubit circuit that makes sense? And then, so the process today would be, okay, define the desired functionality. Let's assume I took this recipe. Sometimes I have pre-existing blocks. So, I want to do an adder. Maybe someone wrote an adder for me. I need to do a QFT. Okay, maybe I can take a QFT block. You try to put all these blocks together, and then you need to optimize them. Both optimize them as well as fit them to the hardware, because you may be saying, my hardware only has 20 qubits. What can I do? The circuit as I drew it has 37 qubits. How do I get rid of 17? Can I use fewer qubits and make it longer? Or my specific hardware has native control Y gates. Can I use those to make the circuit more efficient? Or what would happen if I have more auxiliary qubits, more ancilla qubits? What implementation should I choose? So every one of these blocks is sort of a challenge, both on the block level and also on the system level. On the block level, we spoke about multiple implementations, QFT adder versus ripple adder, more qubits versus fewer qubits. How accurate do you need this to be? Maybe the algorithm calls for approximating a Gaussian function, a Gaussian distribution. The more qubits you have, the more accurate you can make it, but do you need it to be that accurate? And then again, when you put everything together, how deep can the circuit be before it becomes useless? How many qubits do I have? Can I reuse qubits? What can I do about the noise model? And so on and so on. So this becomes increasingly complex to the point that it's just impractical to do it manually. And these issues are interconnected, because if you want to reduce the number of qubits, maybe you have to go back to the block level and choose a different implementation. And so on and so on. So what is it that we do? We have a software platform. We're a software company that allows people to create quantum circuits. And we believe that we can make quantum circuits that perhaps could not be created otherwise. And let me explain, what is it we do? So this is sort of a big sentence from our marketing brochure, but I'll break it down for you. We basically start from a high-level functional model and then turn it automatically into optimized gate-level code. And therefore, you can build complex circuits. So let me take a historical analogy. What you see here on the screen on the right side is an electronic circuit. It's not a quantum circuit. It has, I don't know, 100 gates and or not. Anyone know what it does? I don't. Anyone feel that they could easily change it in a useful way? They could modify the functionality. If this was done by the person that came before you, and now first day on the job and you got the circuit, and your manager says, oh, I need you to add this functionality, you don't even know where to start. Well, this circuit electronically was generated from VHDL code. So in the electronic design world, people developed languages like VHDL or Verilog that define a high-level model of the circuit, a functional model. So when you look at the circuit on the model on the left, you say, okay, even without diving into it, oh, I see that I guess it's an adder. And when I say 15 down to 0, I'm guessing it's a 16-bit adder. So if I needed to make it a 32-bit, at least I know where to start, and so on and so on and so on. And the model on the left gets synthesized into the circuit on the right using software tools like Cadence or Synopsys, companies that have been very, very successful in electronic design. Because when we are running Zoom today, we're running it on computers that have a couple of billion transistors in them. There was no way this was designed manually. It was designed through high-level languages like VHDL. So in a nutshell, we do the same for quantum. We allow you to define a high-level model of the circuit. So here you see basically our definition of a simple Grover search. We defined a constraint. We want this to fit in 12 qubits. Here's a functional block that is a Grover operator. The Grover operator needs an oracle. So we define here an oracle in symbolic terms. A is a quantum register of 3 qubits, and B is 2 qubits, and we want to find A plus 5 XOR B modulo A equals 2. We set here the output format to be Q sharp, and this actually we've taken out by now. But this is a functional model. And if you wanted to change it to make the registers bigger, or to change the oracle, or to do something else, you can imagine that it's pretty easy. And that this model then gets synthesized by Classiq platform into a circuit such as you see on the right. So here you see a block. I'll show you this live in a little bit. You see the adder, you see the XOR, you see the equal, the modulo, and so on. And then you see the dagger operators cleaning them up, and here you see the Grover diffuser in the measurement. If I had to create this circuit manually, it would take me a very long time. If I had to create the circuit this way, using the functional model, it would take me about 2 minutes. So not only can we do it quickly, but we can do other things as well. When the circuit becomes larger, we can work through very many different optimizations. All these things that we discussed. Can I use more qubits or fewer qubits? Can I do a ripple adder versus a QFT adder? Maybe some things I can run in parallel. Maybe if I'm trying to do a Hamiltonian, maybe I can commute the terms and do them in different order and be more efficient. Maybe I can reuse qubits. We explore millions and millions of options to try to find a solution. So where we sit in the protocol stack, we accept the high-level model. What is it that you want to deliver? The constraints could be the number of qubits, could be the native gate set, could be the level of entanglement, it could be the number of C-naughts, it could be many different constraints that might be important to you.
Yuval, excuse me, can you take a quick question?
Sure.
This is really impressive. So it seems to me it's a no-brainer. Why would somebody not use this? I mean, compared to doing it manually. True? Is that?
Well, I mean, I get paid to say that, but thank you for asking. Yeah, I mean, I think this is the way to create sophisticated quantum circuits. Now, I want to just talk just a second about the constraints. The constraints end up being very important when you switch from one machine to another. And that's one of the things that happens in quantum computing today. I mean, what's the best machine for your job? Well, that depends on what you're trying to do, but that also changes over time, because maybe in 3 months, maybe IonQ is going to have a new machine coming online. Maybe Honeywell is going to have something else, and maybe Quantinuum is going to have something else. So we take the high-level model, the constraints, and we synthesize it, and then our output is either Q sharp or Qiskit or IonQ or QIR or Cirq, and then it goes through the traditional compiler or transpiler, and then goes into cloud provider of your choice, Azure or AWS or IBM, and so on and so on. Because we work at the functional level, we can do many more optimizations than the transpiler can do. So for instance, the transpiler doesn't understand what you're trying to do. The transpiler might say, oh, I see 2 consecutive Hadamard gates. I'll just make them an identity gate. I don't need 2 consecutive Hadamards. But we, just to take sort of an off-the-wall example, if we see a QFT block, a quantum Fourier transform block, and then a QFT dagger block, one after the other, we say, well, these are identities, so we don't need those. The transpiler would never know this was QFT in the first place. The transpiler would never say, oh, I can make this calculation different if I have more qubits. So we just are looking at a much bigger design space, and therefore we can deliver solutions that are both easier to create, but much more compact. Just to give you a sense, and so we think we basically automate the process. You just tell us what you want, and then we'll figure out what's the best way to do it. A couple of weeks ago, one popular application of quantum is quantum chemistry. And so people want to find the ground state of a molecule. We took H2O, water, and ran it through someone else's quantum library, and it generated a circuit that's about 6,000 gates to find the ground state of H2O. We executed that on a simulator. We saw what the results are. We put them aside. Then we took the same problem and took it through the Classiq platform. And we were able to automatically generate a circuit that was 3,000 gates, half the number of gates. And executing that circuit yielded the same result as the 6,000 gate version. Why is that important? That's important because, one, if you look at errors and coherence time and so on, then more compact circuits are useful. The other thing is you have limited resources in a quantum computer. So if you're able to make circuits that are more compact, you could fit a larger problem into the same computer. And so in short, and I'll show you a couple of examples, we allow the user to focus on what you want to do, not the how. You can make the circuits bigger and bigger. I mean, we regularly generate circuits for hundreds of qubits just during our testing. Soon enough, there'll be computers that can run it. But for now, we know how to generate them. We can make the circuit more optimized, do it much quicker, so you can go through many more problems. And if you saw the code, I'll show you a couple more examples. You don't necessarily have to be a quantum expert. So, for instance, if I look at what you see here on the left, this is a definition of a finance problem to finding the value of a call option, what's called a European call option. And the circuit on the right is what we generated. But if you look at the left, there's not a lot of quantum going on. Now, everything other than defining the number of qubits and the depth, everything else is finance. And that's important when you get into real deployment, because companies are struggling today. I mean, it's a good outlook for you guys learning quantum, but companies are struggling today to find quantum scientists. So if quantum scientists are rare, imagine how difficult it is to find someone who understands quantum, but also understands finance, or also understands chemistry, or also understands supply chain. So the ability to take some of the quantum complexity out of the design process is very important. This was a call option. Here is, by the way, we deliver everything also in a Python library. So this is a optimization problem. On the left, you see the code. On the right, you see the circuit, and so on and so on. So before I go, and maybe if you want, I can demo some of this for you. I'm wondering if I can answer any questions for now.
There is one question in the chat. So it is, in this case, we care about gate-based quantum computing paradigm, but we can't really apply Classiq on like quantum eigensolvers such as D-Wave, right?
That's correct. We focus on universal gate-based computers, and D-Wave has started building their own gate-based computers, but we don't. We are platform at the moment does not support annealers.
Okay. And in terms of like the final circuit optimization, like I don't know how big the search space is, or is it purely like deterministic? Is there a way to kind of accelerate the optimization process using quantum algorithm, or is it done fully in a classical way?
Circuit generation right now is done in a classical way. We use techniques that are borrowed from chip design.
Okay.
And the reason that's good is we were speaking earlier about how some of the CPUs have billions of gates. So we're comfortable that these techniques could scale to much larger quantum computers. But yes, we optimize it classically at the moment.
Got it.
Yuval,
So-
who else? Where do you guys fit into the larger landscape? Who else like competes with you, if that's the right word? Are there other people taking a similar approach, and how are you different? Or were you going to get to that later?
Well, so when I went to business school, we spoke about competition and competitive analysis and so on. And competition is, you could say, well, who does exactly the thing that you're doing? And we're not aware of anyone that does exactly what we're doing.
Okay.
But hold on, please. But if you need alcohol and there's no red wine, then you could buy vodka or you could buy beer. So there are substitutes. You know, it's not that vodka is a competitor for red wine, it's just an alternative. So obviously not everyone in the world, at least not yet, is using Classiq. They could do this manually. They could hire someone who is going to work very hard to create a circuit using whatever code that they have. But then companies want to be able to port it quickly across multiple computers. They want to create optimized circuit, and they want to develop the internal competency. You know, this is too important to outsource. If I need to paint my home every 10 years, then I can outsource that. I can pay someone to come in and paint. But if quantum is strategic to the company, then you want to develop that expertise internally. Amelia, I think, had a question. I see Amelia raised the hand.
Yeah, well, it wasn't actually Amelia. It's this is Andres. We are in an in-person group, anyways. So I had a question that, from my knowledge, I've seen many new recently published papers. They are trying to create different unitary gates. That's just from the basics. And then, but in their whole circuit scheme, they are only using that one specific block, that only like one part of the circuit that needs something that's created from the basics. I was wondering, given your high-level model, would that be an efficient way to incorporate these things that's built from basics, or how would you deal with that?
So that's a great question. And we do allow designers, whether it's academics or companies, to build their own functional blocks. So for instance, if you wanted to say, I have a CCCC knot, right? Then you could build a functional block that's a CCCC knot, and then we will use that together with our optimization and engine, with our synthesis engine, to try to find something else. So you could actually experiment if that yields better circuits. The other thing that we can do is you could set these as constraints. So you may say, let's see what happens if I don't use CX gates. What can you do? Or I want to use these gates and not others. So you can very quickly explore alternative implementations until you find the one that's best for you.
And there's a question from the chat. So Ronan asked, would you be able to recommend a quantum computer or quantum hardware after the design process? So do you kind of provide that option?
Well, we connect to multiple computers and multiple backends, right? So we both connect to multiple cloud providers like Bracket and Azure and others. And of course, each of them hosts multiple brands of computers. And because it's very easy to go from one to the other using Classiq, it's not uncommon for someone to say, I have this circuit, I've debugged it on a simulator. By the way, we just very recently announced collaboration with NVIDIA, which they have high-end simulators, so you can run even more sophisticated circuit on a simulator. And I'll say, now I've debugged it on a simulator, let's try it on this on IonQ, and let's try it on Rigetti, and let's try it here and there and there. And you can make that switch very quickly and then figure out for yourself which one is best, whether it's noise or cost or speed or whatever it is that you worry about. So we don't make an automatic recommendation, but it's very easy to try different ones using Classiq.
And do you want to ask the question directly?
Yeah, so like in principle, from what you said, from what I understand, is basically this is a efficient way of like writing codes in the backend using software, right? So my question is, you say that in one of the slides you said that it required a lesser number of gates than it does if you write it like on, say, Qiskit or Q sharp or whatever. So like, how does that exactly work? I mean, like, how do you go from, let's say, n number of gates to an m number of gates where m is less than n?
Right. Well, because we optimized it earlier in the process. So if you gave me a complete circuit and just said, well, here's a CASM circuit and now optimize it, then that's not what we do. I mean, there are other firms that try to do that. But we can, and I'll show you in a second how we can say, oh, you have different constraints, you need to limit the depth, you can explore different options and find something that works better for you.
Right. Okay.
Alexandra, I know that you posted a question in the chat, but since it seems like you have a bit more context, do you want to kind of elaborate and then ask the question directly instead of me paraphrasing it?
Yes. Okay. Yes. Sorry for. Yeah, the question was so. It's more related to some experiments we tried. I mean, motivated by the fact that we wanted to compile a large circuit Shor's algorithm with all the multipliers, etc. So we didn't take it at a functional level. We went, as you mentioned, gate-based optimization, and it proved to be a pain, in the sense that the software that we used. And I mean, we had our software built on top of Circ, and we used the optimizers from Circ, or we extended those, and we wanted to compile the Shor's algorithm for error correction, in particular lattice surgery, etc. So then we gave up because it didn't work, and we ended up trying to compile and optimize multipliers because they're a building block, and we failed also. In the sense that at the number of qubits, like about, I don't know, it's I think 256 or 300, around that number of qubits. The number of gates in the circuit was huge because you have quadratic complexity in the depths in the multiplier. And then we predicted that, I mean, using Python as a backend for this quantum software and using the techniques that are available and whatever, we predicted that it's not really feasible to try an optimization run on a circuit because it costs a lot of money. So until the software doesn't become scalable, faster, whatever, it's, I mean, you know that when you are compiling circuits, you do a first run, then you look at the circuit, and then you do a second run and a third run, and you optimize in a loop. So if each loop costs around $10K only of energy costs to run it, then it's not a good deal to try to optimize quantum circuits. So the question was, I mean, this was the context. Now the question is, sorry, is Classiq considering ways of quantifying the cost benefit of quantum circuit optimization? So do you take into account Like, well, how much does, I mean, you optimize small circuits, do you extrapolate and say, well, if we will do the real thing, this is the amount of money it would cost you, and this is what you would save on, I don't know.
Right, right. This is the point where I say, could you repeat the question? Right? No, I heard the question. That's fine. Thank you for it. So we optimize, as you know, we optimize on a classical computer. So of course, the cost of our optimization is much less than if you try to run different models on quantum. Now, we do have an API connection with the various cloud providers. So we could say, well, this circuit, if you were to run it for say 1,000 shots, given the number of gates and the number of 2-qubit gates, and so on and so on, it would cost you X dollars. And this circuit would cost you, more or less. So we can help you with the cost optimization of the actual execution of the circuit, if that's the constraint that you're seeking to optimize on. Does that answer the question?
Not really. I mean, when I mean the optimization cost is like the classical optimization cost. Like you have classical software for optimizing the quantum circuit. So the cost of running the classical computer to optimize the quantum circuit,
I see.
It's like hugely expensive.
Well, I mean, you'll see in a second. I mean, I know that I'm not going to run very large circuits today, but our process takes a few seconds. So a few seconds of an Amazon EC2 instance is not terribly expensive. So I think that the optimization is really the cloud costs of the optimization is really negligible compared to the actual execution cost on the quantum computers.
Okay, so and this is the argument you make that it's the functional optimization that reduces this cost and not the gate level optimization.
Yes,
I see. Okay,
very much. So let me fire up the demo, and of course we can happy to continue to take questions as we go through it. So as I mentioned, we run both VS Code environment as well as we run both VS Code as well as Python. I'm going to show you the VS Code Visual Studio Code, and let's go through just a few simple circuits and sort of increase them in complexity a little bit one by one. This is a state preparation block. So we have functional blocks. So for instance, here you have state preparation. State preparation is the process of initializing qubits to a certain value. So that ends up being the beginning of many algorithms. So we have the functional block that says, here I have, say, 8 probability mass function values. So I need 3 qubits. And here I put the constraints. We say, oh, we want to use 4 qubits total, no more than 200 total depth of the circuit. And let's say we want Q-sharp output. So this is live, meaning that these are not circuits that I prepared ahead of time. When I hit generate, it's sending this circuit to our cloud. And here you go. Here's a quantum circuit that implements what we just did. By the way, I forgot to ask, is the text large enough, or do you need me to make it larger? Large enough? Okay, so here is the quantum circuit. So I have 4 qubits, and you can see everything that's going on here. And here is, by the way, the Q-sharp code that implements the circuit. You could execute, and obviously you can say, oh, this is 400 lines of Q-sharp. We just created them in 2 seconds. Obviously, it would take me longer to do it manually. Let me run it again and say, oh, well, I instead of Q-sharp, let's do chasm output. And getting the same circuit, and here's the chasm output. One of the things we can do here is analyze the circuit. So I have the chasm output, selecting the one I want to analyze. And what you see here is it gave me a whole bunch of interesting information about the circuit, but specifically, if you look here, says this circuit is 78 deep, and I'm using 112 gates, and I'm using 46 multi-qubit gates, and so on and so on. And these are, by the way, the native gates that I'm using, CX and U. But let's assume that this was too much for me, that I said, well, state preparation is nice, but I need to save coherence or error. I want a shorter circuit. I don't want this large circuit. So one of the things we can do, one of the parameters I didn't show you here is the accuracy. So here we define 1% accuracy, meaning that the circuit needs to generate these values within 1%. But if I lowered this, I make it less accurate and generate the circuit again, now you can immediately see that I got a smaller circuit, a shorter circuit. So that as a designer, it allows me to explore different options. Now, you guys are all experienced. So let's do, so I don't always show it, but for you guys, maybe it's fun. So I showed you state preparation circuit. And now let's assume I have 5 of them. So each of these blocks initializes 3 qubits using 1 auxiliary qubit, using 1 ancilla qubit. So I now have 5 blocks. Here's 1, and here's the 2nd, and here's the 3rd, and here's the 4th, and here's the 5th. And I defined that I want to fit this into 20 qubits. So that's easy. I got 5 blocks. 3 plus 1 is 4. 4 times 5 is 20. If I generate that circuit, I'm sure you know what it's going to look like. It's going to, I'm showing sort of high-level functional blocks. So I just have 5 independent blocks. Each of them is 1 state preparation circuit. And just so for your information, qubits 0, 1, and 2, or input 0, 1, and 2 at every block are the 3 qubits that we initialize, and 3 is the auxiliary, the ancilla qubits. Well, what if I wanted to do the same thing, but with 16 qubits? So I want to initialize 15 qubits, 5 times 3, with just 1 ancilla qubit. How would I do that? How does that work? Well, is that possible? I don't know. Let's try. So I just set the constraint. I change the constraint and say I need 16 qubits. Now I'm going to generate quantum circuit. And now here's what happened. I'm going to zoom in and then show you a little bit more. So you see that I still have 5 blocks. And so for instance, let's take the top block. It's 0, 1, and 2. These are the qubits I want to initialize. So they go all the way to the end of the circuit. But then qubit 3 then goes into the next circuit. And qubit 3 here goes into this circuit. And qubit 3. So what's happening is that the system automatically uncomputes and reuses the ancilla qubit. So it says, well, this is a qubit that I don't need to measure. So I can clean it up and reuse it, and therefore we are able to save qubits to fit the same functionality in fewer qubits. And one of the things I can do here, I call this Burke, and we have what's called an interactive circuit. I'm going to open this for you, and I may need to move that window over to the area that you're seeing. So now you see these 5 blocks, 1, 2, 3, 4. This is the 4th one, and this is the 5th. And now I can go into every one of them and see what's going on inside. So I can sort of zoom in as deep as I want and see what has the system created, how is everything being done, where is the cleanup, and so on and so on. So I could go from very, very high level all the way really to the individual gate level on this. So this was sort of the multi-qubit, the multiple state preparation. Let's look at something else. and let's do Grover. So you all know Grover, and a Grover search needs an oracle, right? It needs a function that says this is the right solution, this is the incorrect solution. So here we're basically saying to the system, look, maybe I overdid it here. This might take a little bit more time, so let me just clean that up just a tad. So here I'm defining, and you can see I'm doing this live, so who knows what will happen, right? I'm defining 3 registers, A, B, and C. So A is a 3-qubit register, B is a 3-qubit register, C is a 3-qubit register. And I've defined the oracle simply as a arithmetic expression, just like you would define this in Python. Check that A plus B and C and 7 modulo 8 or 4 and C equals 4. Let's see if I can generate a circuit from here. And so now it's going to run and it's going to explore various options on our cloud. It may be that it will fail. It may be that it will succeed because but in this case, it succeeded. So here you have both, CASM code, this is only 900 lines. But now you see the Grover circuit. And you can see each of the blocks. It has an addition, and then it has the bit end, and then it has the addition, and then another bit end. I can go here and check them out. I'm sure probably one is the C and 7, and the other is the 4 and C. And here it decided to do 2 things in parallel. And here it has the cleanup, and here it has the Grover diffuser. And just like before, I could go into that Grover circuit that I just created. This is live with today's date. I can open it in a browser. I could explore exactly what's going on inside. Oh, here's an adder. Looks like the system chose a QFT adder. What does a QFT adder look like? Well, it looks like this. Okay. Here is the block that says equal 5. Well, what does that mean? Okay, so I see, here's how that was implemented. Now, you don't need to go into this level of detail. If you're a designer, you might say, I'm perfectly happy with this, and now I can execute it, I can run it, I can see what the solution is. But if you wanted to, you could see what the gate level implementation is. Or you could say, okay, now you're using 18 qubits to do this. Could you fit this in 10 qubits? Could you fit this in 15 qubits? So as a designer, you can have a lot of flexibility in looking at different options. Does that make sense? Is that boring? I mean, give me some hints on what you'd like to see next.
Looks like magic.
Looks like magic. Very good.
There's a question in chat. Ronan is asking, is there a way to get it to test for a minimum number of qubits?
So you could do that in multiple ways. So if I go back to that. Where was it? Was it this one? No, it was the multiple load. So I showed you how to do it in 16 qubits, right? I initially showed 20 qubits and then I said 16 qubits. Well, let's see what happens if I define 6 qubits. I want to initialize 15 qubits, but I only have 6 qubits. And this is sort of, you don't need to run something to know that it's not going to work. But if I run this very quickly, you see an error message here. Constraints are unsatisfiable. We have not been able to find a solution that does this. Now, if you run this in Python, maybe a good opportunity to show you this. So I'm going to bring up a window that has our documentation. And it talks about many different things, starting from how do you get started to begin with, and you look at these, sample programs. We've got a lot of different sample programs, whether it's in optimization or Grover search or financial analysis, how to execute. But each of these example programs, for instance, I don't know, let's take amplitude estimation. You see that it has both the language description that's useful for our VS Code extension, but it also has the Python version. And in Python, you basically define the circuit in this case, and then you call what we call sort of model designer, make this, or sorry, the synthesize this circuit. And this can return an error code. So it's perfectly fine to say, let's start with 20 qubits and run a loop 20, 19, 18, 17, 16, and then that's how we can find the minimum number of qubits that we can find a solution for, or whatever it is that you care to optimize for. And we also have developed a bunch of sort of vertical specific applications. If it's chemistry, if it's finance, if it's credit risk analysis. To the question you guys asked earlier, here's how we can create custom functions. So this is a trivial example that controls Z-gate, but even here you see that we define two different implementations, and we let the engine choose which one is most appropriate at that given time. Or here's a ripple adder. So I mean, you can define your own blocks and then get them to run within our code. I hope that answered the question. We can put blocks together one after the other. Here's an optimization problem. It looks like I've been working here on other things, but constraint satisfaction, what's called sometimes 3-SAT or B-SAT, is a very popular optimization problem. How do you find a set of variables that meets a certain criteria? We can solve that as well and create quantum circuits for it. If you're doing chemistry, here's something that would generate a ground state Hamiltonian for chemistry. For doing finance, optimization, and we continue to add modules, and our users continue to add modules, whether it's going to be a machine learning model or other things. So let's just take a step back and see what we've seen. In the last 10, 15 minutes, we generated, I don't know, a dozen circuits. How long would it take you, the best of you even, right, to generate a dozen circuits? Would probably be more than 15 minutes. How long would it take you to optimize it? How long would it take you to move from one machine to another? And I think that our platform allows you to, instead of programming in quote unquote assembly language, focus on what is it that you want to achieve, and we can help you the best way to realize your quantum vision. Varun, I see you have a question.
Yes. So I saw like in the constraints, it's just usually like width and depth in most of the circuits. Is gate sets also some of the constraint that is possible right now or something in consideration?
The constraints, so we have many different constraints that you could enter. You could enter the number of qubits. You could say, I want to use specific gates. You could say, I only have 17 C0 gates, so deal with it, figure some other solution. We are now working on integrating the noise model from the actual computer. So for instance, if you had a 20 qubit computer and we knew that 4 qubits are noisier than the others, then we could say we might recommend a solution that uses the 16 quieter qubits, even though if we didn't know anything, we would use a 20 qubit circuit that's a little shallower. So there are many different constraints that you could take, and our algorithm tries to find a solution that meets these constraints while delivering on the functionality that you want.
Okay. Yeah, because like in the examples I saw, like most of the times like width and depth. So
right.
Thank you.
I know sometimes I forget that we're doing a demo and not training. If we were training, then we'd go deeper into many of the constraints, and it might take more than 15 minutes to look at all the wonderful things that we can do with the system. We also have an analyzer tool that allows you to look at things like connectivity, which qubits are connected to what, heat map, meaning which qubits are busier than others, and maybe you want to balance things out, and so on and so on.
All right. Yeah, that's very interesting. Thank you.
Sure. Victor, I don't know how we're doing on time. I don't want to.
So technically, we should be wrapping up. How much more content do you think?
No, I think I'm about done. But if there are questions or specific things that you'd like to see, I'm happy to try and show them to you. But as far as slides and the sort of the standard demo, I think we finished that.
Okay, perfect timing then. Any question? I mean, I think we've been having a pretty good discussion along the way. Yeah, I think Andres or Amelia has a question.
Yeah, sorry, it's me again. So earlier when you talked about the noise model, I want to follow up more on that. So does this model that Classiq is currently working on heavily relies on the fault-tolerant quantum computing, or is it more a NISQ-era applicable scheme? Because I know many companies nowadays, they just, I kind of don't want to say give up, but they focus more on the NISQ-era development. So yeah, what do you think?
So yes, when I said noise model, I was referring to NISQ-era noise model. You can certainly use our software to explore constructs that do error correction as well, and debug them. And these are some of the problems that we're thinking about, we're working on. It's easy to. I don't want to say it's easy, but it's feasible to debug a 30 qubit circuit with a classical computer, because you could simulate it on a classical computer. What happens when you have a 300 qubit circuit that you can no longer simulate? How do you debug that? And so there's some interesting questions that we're working on that front. How do we code and take advantage of error correction? So we think we live in exciting times, because a lot of things are happening. A lot of people are trying new and exciting things. We certainly, because we're in the NISQ area, then we do allow all these hybrid algorithms. I mean, I haven't shown you VQE or GUAO and so on, but certainly you could code them with our platform as well. And can't wait to see what the future holds.
Yeah, do you think it will still have an advantage for the this high-level functional model, even if fault-tolerant? Let's be not optimistic. Like even if fault-tolerant is not reached in like next few decades, do you still think this can have an advantage?
Absolutely, because we can create circuits that are more compact and more efficient, and therefore would perform better even in NISQ-era machines. We can allow people to design. One of the things you look at quantum algorithms in general, and you say, okay, well, there's Grover and there's Shor and there's HHL, and there are not 37 quantum algorithms. They're more like 7. One reason that's been so difficult to create them, but using a system like this, perhaps it will be easier for people to create sort of the next generation of quantum algorithms, whether hybrid or pure algorithms. Because if today you're spending most of your time at the gate level, and we relieve you of that, then you have more time to spend on the creative side. So hello at Classiq.io is our main email address. I'm Yuval at Classiq.io. I also publish a weekly podcast with some interesting guests, anything from, Paul from Cold Quanta to a couple of weeks ago was the former head of the National Security Agency talking about quantum geopolitics. I've got an episode coming up with a professor of quantum music. So there's a whole whatever you're interested in, I'm hoping you can find it both on our website as well as on the podcast and blogs, and would be happy to keep in touch with any of you.
Awesome. Did you say quantum music or did I hear wrong?
I did say quantum music.
Okay. Is it DJ Spooky?
It's the person. Yeah, this is Professor Eduardo
Okay.
Miranda.
Got it. Got it.
Does quantum music, and it was fun. I mean, a little bit unusual for the usual topics that we talk about, and but he's got quantum machines, quantum computers, both suggesting new melodies, or what should I play 4 notes and what should the 4th one.
Yeah.
He's also trying to do real-time accompaniment. So you play a sax, and then the quantum computer sort of figures out how to support you that. He's got some cool YouTube videos that show that. So it was a really fun episode.
No, that sounds so sick. Well, thank you so much for your time today. I think this is incredibly informative, and also sparked a lot of really good conversations. And so what happened next is I will share the recording with the community, and feel free to forward it or share with your network. I'm not sure if you can tell how tired I am right now, but it is close to 2 a.m. right now on my end. So I think, this is such a great conversation, and thank you for your time.
So thank you, Victor, and good night to you, and thank you all.
Yeah, have a good day. Bye, guys.
Montreal.